Hi everyone. Now we are going to discuss on the half-wave controller rectifier. A half-wave control rectifier is nothing but it is using a single thyristor on an HWCR which is in series with your supply source. So your supply source is nothing but an AC source. You have your thyristor and then you have your load, and here your load is nothing but a resistive load which is denoted by R. So here your input supply voltage is Vs, which is nothing but Vm sin omega t, that is nothing but which is shown in this particular waveform. So therefore, since the load is nothing but a resistive load, it is a half-wave control rectifier connected to a R load. That is the analysis which we are going to make over here. And we will be denoting the value of your current which is flowing through the load as I0. That is your load current I0. And V0 is nothing but your output voltage. And the voltage across the thyristor, so this thyristor is indicated by T, so the voltage across the thyristor is Vt. Now the HCR will be conducting only when the anode voltage is positive with respect to the cathode and also a gating signal is applied. So during the time from 0 to, so this is 0, this is pi, this is 2 pi, and this is 3 pi, so on. So from 0 to pi and from 2 pi to 3 pi, the thyristor T is always in the forward biased condition, and the thyristor will get turned on anytime from 0 to pi if I am giving a gating signal, and that gating signal at which I am applying is nothing but the firing angle alpha. So alpha is nothing but the firing angle at which I am going to fire your thyristor, or you are going to trigger on your system into conduction state. Now I am going to fire my thyristor at an angle alpha, and in order to fire my thyristor I need to give the gate supply voltage. So that is denoted over here. So that is nothing but, this point is nothing but your Ig. So I am going to trigger on the thyristor during when the thyristor is forward biased. So this happens in the time from 0 to pi and also from the instant from 2 pi to 3 pi. So between pi to 2 pi you don't need to give the gate pulse because the thyristor cannot be turned on when the device is reverse biased. Now I am going to plot the output voltage. So this angle alpha, so this is nothing but your angle alpha. So this is nothing but your angle alpha. From 0 to alpha, the thyristor is in the turn off state. Therefore, your output voltage V0 will be equal to 0. At the instant when at alpha, when the thyristor is getting turned on, the entire input voltage Vs will be appearing across the resistor R, because the thyristor will be acting as a short circuit because it has gone to the conduction state. Therefore, from alpha to pi, the output voltage is nothing but Vm sin omega t. So therefore, I can plot my output voltage as like this. So this is my output voltage V0, that is from alpha to pi. At the instant pi, the system has gone to the reverse biased condition, and the current here is nothing but I0, which is nothing but the current through your load resistance R. And for a resistive load, the I0 will be always in phase with your voltage V. Therefore, when the voltage gets reverse biased, that is at pi, the voltage becomes 0 and then it goes to the reverse bias condition. That time the current has also reached to 0 and therefore the system will go to the turn off state because the anode current has come to a value much below the holding current and therefore the system gets turned off. So two conditions are met and the device goes to the turn off state. Now we'll be plotting the output current I0. So we have already mentioned that the current I0 will be in phase with your output voltage V0, the output voltage V0, and the amplitude of your current I0 will be nothing but Vm sin omega t divided by R, and therefore I can plot my output current as the same value of the same voltage waveform V0 but at a lower magnitude, so from alpha to pi. So the same thing will be repeating in the cycle from 2 pi plus alpha. So this is again your alpha. So from 2 pi to plus alpha to 3 pi, the output voltage will be like this and the output current will be like this. So for V0 and I0, they are in phase with each other, but the I0 value is lesser than your V0 value. Now at this condition we should also see how the waveform across the thyristor will be looking like. So we have to plot Vt. So Vt is nothing but the voltage across the thyristor. When the thyristor is in the off condition, then the entire voltage will be applied across the thyristor. When the thyristor is in the off condition, that means it is acting as a closed switch and therefore the voltage across thyristor is 0. So first let us plot how it is behaving or Vt during turn of state. From alpha to pi, the thyristor is in the turn on position and therefore the thyristor voltage is 0. So that is this condition. And from 0 to alpha, the thyristor is in the off condition and therefore the entire voltage of the thyristor is nothing but your input voltage. And from pi to 2 pi, the device is reverse biased and therefore the thyristor is in the off condition and therefore the thyristor voltage is nothing but your supply voltage V0. And from 2 pi to 2 pi plus alpha, the device is forward biased but the device has gone, it hasn't gone to the conduction state. That means it is remaining in the off condition. Therefore the thyristor voltage is nothing but your input voltage. So this will be again repeating like this. So if I am overlapping your V0 and your Vt, you will be getting your input supply voltage Vs itself. And here we can also mention the instantaneous values of various voltages. So at this instant for V0, this is nothing but Vm sin alpha, and the maximum value of your output current I0 is nothing but Vm by R. So this is the total working principle of a half controlled rectifier with an resistive load. The voltage and the current will be in phase with each other and the thyristor voltage will be 0 when the device is in the conduction mode, and your output voltage is available only when your thyristor is into the conduction state. That time the thyristor will be acting as a closed switch and the entire supply voltage will be coming across your resistive load R. The total time period of the circuit is given by T is equal to 2 pi by omega, and here from here we can define the circuit turn off time Tc, and the device is being reverse biased from the period from pi to 2 pi over here, and therefore Tc is nothing but 2 pi minus pi divided by omega is nothing but pi by omega. So Tc is nothing but pi by omega.